Are you able to hear me, VAT, JPR?
Yes, ma'am.
Okay, fine, all right. So we start from, yeah. So continue with what we left the other day. So to summarize, we had talked about vector fields, where the magnitude and direction could be space dependent. Then we talked about line integral, surface integral, volume integral operations. We also spoke about the operations of, oh, we also spoke about the operations of gradient, tells you the rate of change, divergence, which how much is the vector diverging from that point. And then we used curl operator, which again the answer is a vector, which tells you by how much is the vector rotating about a point. Now, with this understanding of basic vector calculus, let's go on and try to see if we can see our ultimate aim was to get to Maxwell's equations. And why are we doing Maxwell's equations? At this point, the purpose is to solve the transmission line problem completely. We have done a circuit theory solution. Now we want to do a complete solution by finding all the transmission line parameters from the basic electric and magnetic. So come back to electric field. We discussed what electric field is in the last class in context with explaining to you why would you have a divergence. So in that context, I said that if I have a charge q in space, if I bring in another charge small q at a distance r in a direction specific, in a specific direction to r, I said the force experienced by q, the small q, is 1 by 4 pi epsilon 0 q by r square in a direction which is pointing to the unit vector r, and this is nothing but a restatement of Coulomb's law, and it is from here that we defined electric field E as the force experienced by q, say the limit as q tends to 0, f over q is your electric field. We also discussed the other day that if I have a charge plus q in space, and if I keep plotting the force at every point around q, you realize that for points which are very close to q, your r is small and so the force is large. So you will have large magnitude. And if I draw a vector whose magnitude is proportional to this force, or magnitude is proportional to this electric field, and whose direction is in the direction of the electric field, I get something like this. And if I do this all around the charge q, we would start seeing, right? It's not that these lines are physically present around this charge. These lines are just representing the electric field vector at that point in space. Now, we used this idea to understand what is divergence. We said this is a case where if I take the total outward flux, or if I take flux around through a volume, and if I shrink that volume to delta V tends to 0, that is the divergence at that point. Now, we go on one step saying that, so this we used as an example for a large divergence. I also said the other day that you can imagine a large negative divergence by considering a similar situation with a minus. Now we are going to go on to say that the total electric flux, remember what was flux? Flux is defined by that surface integral. So electric flux would be the surface integral of the electric field. The total electric flux through any closed surface, considering a closed surface like this, where am I putting the surface? Through a closed surface around, well, it need not be around the charge. I can put any closed surface. So if I imagine this, and if I am calculating what is the total electric flux, remember how to calculate flux? Flux was surface integral of that vector field over that area. So if I do the total electric flux through the entire closed surface is equivalent to the charge, the total charge enclosed by that surface. This is very intuitive because, you know, if you consider this example, why do you have a flux? So what is the meaning of flux here? I calculate, so I have this area, I have electric field going, diverging from this area. All what this statement says is that if I calculate the field times the area, that of course has to be related to the charge, because the charge Q is the cause of that field, right? So the statement simply says that the total flux around closed area is equal to the charge enclosed by the surface. Mathematically, it means that the flux, if I say flux is psi, and we are talking about the flux due to electric field. So the flux psi is E dot ds from our definition of flux around the closed surface. The circle indicates it's a closed surface. That is equal to the charge enclosed by the surface. Now, this is the statement of the first Maxwell's equation, which is also referred to as Gauss law. In fact, this was known as Gauss law for a pretty long time to honor Gauss, who actually figured a way to measure electric field and magnetic field, right? It's when Maxwell formulated or consolidated all the laws of electromagnetics, this came out to be the first law of electromagnetics. It simply says that the total flux is charge enclosed. Now, yesterday when we spoke about divergence, we also talked about Gauss divergence theorem. We inverted the definition of divergence, right, and said the flux, divergence is the limit. What did we say divergence as? If I take the flux around a closed volume here, divergence is just the limit that, in the limit that the flux per unit volume, in the limit that the volume tends to 0. So we had said if I invert this differential relation, I get surface integral A dot ds, which is the flux, that is nothing but volume integral of divergence. I'm going to be using the same relation here and claiming that this flux should be equal to, must be equal to the volume integral of the divergence dV, which means if I take the divergence, or what was divergence, it told you a magnitude of by how much is the vector diverging out. If I take the volume integral, that should also be equal to Q enclosed. I have just modified the left hand side. Now, if I say rho v is the volume charge density, why am I introducing volume charge density? I am introducing that because all the charges that are available in nature are not necessarily discrete charges. Discrete charges are of course possible, but the charges that appear in nature, they need not be discrete. You can't find charges always as, accumulated at different places. So there could be places, conditions, situations where I can have a volume which is fully charged with a volume density rho v. What is the meaning of volume density rho v? If I get rho v in a volume dV, I do a volume integral, I get the total charge enclosed. I am just trying to say volume charge density is the charge per unit volume if there is a discontinuous distribution of charge. So if I do that, if Q enclosed is actually represented by a continuous charge distribution, then the Q enclosed can get calculated this way. I substitute this here, I get, remember the left hand side is a volume integral, del dot E, divergence E dV is volume integral rho v dV. Now if I operate both the left hand side and the right hand side over the same volume, I can get rid of this integration and say del dot E is rho v. This is the point form of Gauss law. We had an integral form written earlier which said the flux closed surface integral E dot ds is equal to the charge enclosed, and now we have the point form. This is the integral form. All these Maxwell's equations, all four Maxwell's equations, you could either write it as a point form or as an integral form. The question that typically crosses our mind is, both point form and integral form are saying the same thing. It's the same Gauss law, but written in two different forms. Question that usually crosses our mind is, given a problem, which form would I use? Should I use the point form or should I use the integral form? Which of these equations would apply given a situation? And the answer to that question is, well, it depends on what situation are you trying to apply. Let us say if you have a situation where you have, for example, a boundary. This side is maybe a dielectric, or it need not be even a dielectric. Let's say you're trying to apply it where a capacitor. I'll give you a practical example. You have a plate of a capacitor, right? This is one plate of the capacitor, and there is some charge density rho v in that plate of the capacitor. Now I want to know what is the field here, or maybe if you can think that the sheet is infinitesimally small in thickness, you can say there is a surface charge density rho s. On the surface there is a distribution. If I were to find out what is the electric field for at a distance, and this is the plate and this is air or some other. If I want to know what is given this, I have changed boundary. I have changed the medium. From metal I have gone to air. In that case, what I could think about is take a surface, part of which is in air, part of which is in boundary, and you can imagine which form should I use. I will apply this over this surface. I will apply Gauss law around the surface, which means I'll have to do a line integral around the surface, which means I will use the integral form. So whenever I am at a boundary, I am trying to figure out cases, issues where one part of the medium is different, the other part is different, the properties of the media are different, I will use an integral form. But when do I use this? For example, the same capacitor, I have, let's say the plates are infinitesimally big, and I want to know what is the electric field inside. I have plus Q here, I have minus Q here. I am not talking about the boundaries, I am talking about well within the volume. I want to know how the electric field is behaving from plus to minus. Is it decreasing, increasing? What is the nature of behavior? So I am well within a volume of the same material. I want to know the nature of the electric field. I would use the point form. Same with all Maxwell's equations. As a general rule, we will be talking about point forms and integral forms, but as a general rule, you will use point form when you want to solve for a given point, at a given point within the same medium. Whereas you would use the integral form when you are at the boundary, so that you can imagine the infinitesimally small volume or the surface which is partly within one medium and partly within the other medium. So that this is independent, the laws are independent of the nature of the material. It has to hold good everywhere. So you will be able to solve for situations at the boundary using the integral form. Alright. Now we have discussed the point form and the integral form for Gauss law. Now the next thing is, you should also remember that well, there is an error here, and the error is the following. See, when I write it this way, there is a small problem. The problem is E, as you know, is dependent on the medium. So if I write it this way, it actually depends on what kind of medium I am using. So Gauss law is not usually written this way. This is just for your understanding from E field that I started writing this way. But Gauss law gets written not for E but for D, where D is your electric flux density. Because the total flux becomes E dot ds only if E is the flux density. But E is not flux density, it is D that is flux density. So I should actually correct it as D dot ds. And as I said, the reason is electric field intensity and flux density are slightly different. It's the same if you are doing everything in vacuum. But D is, so you have this in vacuum. Now if it is a medium, this epsilon 0 gets replaced by epsilon 0 epsilon r, where epsilon r is the relative permittivity of the medium. Now it simply means that my electric field depends on, or it changes when I change the medium. And we want a Gauss law or this law to be independent of the type of the medium. You want to be applying it everywhere. So electric flux density is a vector which is defined as epsilon E, where epsilon is epsilon 0 epsilon r, so that D is, you don't have this, so it will be simply 1 by 4 pi q over r square unit vector r. For unit charge q, the force is 1 by 4 pi. After you multiply with epsilon 0 epsilon r, this would be the electric flux density. And when you say electric flux, it has to be D rather than E. I wrote E initially just to associate this with what we did in the last class. So the Gauss law, when you write, it has to be for D. This is D, and this relation has to be for D, del dot D, del dot D dot D. Now I'll remind you again, the idea is the same, except that if you remember this relation, D is epsilon E, and this epsilon is a scalar for isotropic media. Now you will have cases of anisotropic media where epsilon is not a scalar, it becomes a matrix, where you apply electric field in one direction, the displacement could be in another direction, and so on. So let's not get into all that. At this moment, D is linearly related to E. So now that we have the correct relation for Gauss law, which is del dot D is rho and surface integral D dot ds, the flux density is Q enclosed. We move on to define what electric potential is, the point form and the integral form for the potential. So let's say there is a region which has some electric field because of some charge placed somewhere. In this of interest, there is an electric field. What does this mean? It means that if I place a unit charge here, that is going to get pulled in the direction of electric. If I place another unit charge here, it's going to get pulled in this direction of electric. Which means if I were to move a charge from, let's say, this point to this point, say A to B, it is not along the electric field, at an angle theta, for example, with respect to the electric field, it is like saying that I have gravitational field around me, and the gravitational field, the direction of gravitational field is in the downward direction. So if I were to drop something down, I don't have to do any work. The work is done by the field. Whereas if I were to lift something up, I have to do some work against the gravitational. Or if I were to lift something at some mass at an angle, again I am doing a work which is against the field, but now my work is at an angle, in the sense the work that I need to do, the displacement I am doing is at an angle. So my work is force dot displacement, so which means it is Fs cos theta. The same idea here, instead of gravitational field which is in the down direction all the time, it is electric field which can change its direction depending on where your charges are. So if it is gravitational field, as I said earlier, this is the direction of G, and if I were to move something from, let's say, the surface of the earth upwards, I have to do work against the gravitational field. And you know that that work which is done on the body to lift it up from the surface or take it through a height is what you call as the potential. Similarly, the work done dW on a charge Q, a test charge Q, to take it through an elemental length dl. This elemental length has a direction because I want to specifically take it through this direction. What would be the work done? I have to give a work which is equal and opposite to the electric field. Otherwise, I will not be able to move it. So this work done, oops, all my field vanished. So this is my electric field, and I am talking about moving a charge in this direction at an angle theta, and this is my elemental length. And work is force dot displacement. And what is the force here? The force experienced by the charge Q in an electric field. You know that the force experienced by unit charge is E. So the force experienced by the charge Q would be QE. That is the force dot displacement. Displacement is dl. So that dot product I can write it as dl cos theta, and to represent that this is the work done against the field, because QE is the force experienced by the charge. I want to put a work against that, so this is minus. And electric potential is that work done per unit charge. So electric potential dV is minus E dl cos theta, or I can write E dot dl. Remember, this is a scalar, the dot product, the work done, the scalar. So if that is the case, what will be the potential? If I were to go from, so I spoke about the infinitesimally small work done to move this charge through an infinitesimally small distance dl. So what would be the to be? That is not the minus sign I missed here. So that is nothing but integral of this over the line, over the path through which I am moving the charge. So this is integral a dot a to b e dot dl. This is one way you can define, this is the way you can define potential. Again, this is the integral form. You will also get to write down what is the scalar form, the point form. The point form actually you can write it from here itself. dv is minus e dot dl. Remember our definition of directional derivative of gradient. We had discussed that a differential dv can be written in terms of gradient as dv equal to gradient v dot dl, because gradient represents, gradient is a vector whose magnitude represents the maximum rate of change and the direction represents the direction in which the maximum rate of change happens. So if you want to know what is the, if you want to know what is the change in a given direction, you take the projection of dv along that direction. So that is exactly what you want. You want to know what is the change in v in a direction dl. So you take the projection of gradient v in that direction. So equating these two, that if I keep the element the same, my E is minus gradient. This would be my point form. Simply means if at a point if I know V and I want to calculate E, I would use minus gradient V. But if I want to do it in between media or along a length, along a distance, I would use the integral form. Alright. So that defines the potential. The next thing to do in that sequence is what is the effect of field? So let us say I have an electron in a medium in a specific direction. It means that, as I said earlier, if I were to forcibly move a charge in that region containing electric field, I need to do a potential, I need to do work, and that work is stored as potential in the charge, and that defines the electric potential. But suppose there are some, charges plus minus present already in the medium. For example, where can you think about a region where there are a lot of ionized charges floating around? Ionosphere, for example, right? The upper layer of atmosphere where there are, the solar radiation has ionized all gases, and the atmosphere contains a lot of ions, applying an electric field there. What would happen then? This is the direction of electric field. There are no other forces acting in that region. Naturally, the positive charges will start moving towards the electric field. Negative charges would start moving away from the electric field, because as by definition electric field is a force experienced by unit charge. It's given that the field is in this, that the force experienced unit positive charge is in this direction. So what happens? All the positive ion starts moving in one direction, negative ion starts moving in another direction, creating what we call as an electric current. So electric current is nothing but the movement of charges in the presence of electric field. Now you can think about electric current in three different contexts. In one context where everything is free to move about, the charges are all free, it's like in an ionosphere situation. Another situation is maybe inside a vacuum tube, you have two electrodes, you have and you have a low pressure gas there, you have ionized the gases, all the ions in the tube can actually start floating, this giving rise to a current. So that case the current is called as convection current, right? You can also think about electric field applied across a conducting wire. Let's say this is my conducting wire. This is not convection current now. You have free electrons in the system, but that are bound to the atom. Here the free electrons are able to move from one point to another. They actually conduct, they actually cause the conduction, the electric current moves as a conduction. So that mechanism by which inside solids, inside good conductors, electric current flows is conduction current. Is there any other form of current? There is one more current which we refer to in electromagnetics, which is called displacement current. We will come to displacement current a bit later. Let's just talk about conduction current and convection. But in general, these are the three types of current which is usually referred to in electromagnetics. Now, conduction, talking about current now. The way to quantify current is through, of course we know current is rate of flow of charge, delta Q by delta T. But the way current gets quantified is through current density because this is not really sufficient. It does not tell you the direction of flow of current. It does not tell you whether there is a space change, let's say in this region, whether I have more current here, less current here. It doesn't tell much information if I just say dq by dt. Even though elementary, that's a very good definition way of looking at current. But current density is exactly what quantifies. And what is this current density? Current density is the current through unit normal area at that point. Current density is a vector, it's again a vector function. So current density at any point, current density at any point so I can represent current density in ampere per meter square. What does it mean? If I have 5 ampere per meter square, simply means that at this point, if it is 5, and remember it's a vector, which means it will have a direction. It means that like a unit area normal to this direction, the current is 5 ampere per meter square. So to give an example, if the current density is a vector of length this much in this direction, simply means that this point I have to think about a normal to this vector and the current crossing that unit area. Remember, this area is not area in any direction. It is the area that is normal to the direction of propagation current. Through that is 5 ampere per meter square. That's the mean. Which means delta I. So if I think about an area, this is my J. If I take this total current, total J times area, that will give me the current. But if the current density is in this direction and I want to know, let's say I want to know the current in this direction. I have an area in this direction, I want to know the current through that area. Then I have to take the component of J along that direction. So my delta I is actually J dot ds, current through any arbitrary area. So my I is integral J dot ds. This is a more informative definition of current. It's also telling you, in addition to the magnitude, in a way it tells you what is the direction. Even though current is a scalar, it does not have direction. Current density gives you more information about the current. So this is the total current. Flowing through a given surface. So to explain this, let's say I have a conductor like this, and I am considering the area of cross section of the conductor. I want to know what is the current flowing through that conductor. It is not necessary that the current density has to be in this direction. It's not necessary. Depends on how we apply the field. If I apply a field in this direction, my current density is actually in this direction. So if I take an area like this and try to calculate what is the current density, it's actually 0. Because my surface normal is in this direction, my current J is in this direction, surface normal is in this direction, J dot ds is 0. That is where the definition of current density or understanding of current as a vector becomes important. If I just say I is 0, it doesn't convey anything. If I say I is 0, it simply means that the current is 0. But in this case, there is a charge, could be a charge flow, there is a current flow, it's just that it's in this direction, right? This is something that is useful. Now, if I talk about, let us say, a little more in detail, let's say this is my conductor and I'm talking an area, rectangular cross section. Conductor has a rectangular cross section, right? Talking about two areas which are delta y apart. Let's say the area that I'm considering infinitesimally small area is delta S. From my definition of current, it is delta Q by delta T. And let us say rho V is the volume charge density in this medium. I have not said what medium this is. It could be a conductor, it could be an ionosphere, right? This is in general, where there are some charges, there is some volume charge density. Need not be a conductor. Then what would be this? It would be rho V is volume charge density. So if I consider this unit volume, or this is not unit volume, consider this volume within which I can find how many charges. The charges would be rho V times delta S times delta y. Because delta S delta y is the volume, rho v is the volume charge density. So this is volume charge density times the volume divided by delta. And as the charges are moving, I can write this delta S is not what is changing. I am considering a specific delta S. So I could write this as u, which is nothing but the velocity of movement of charges, velocity of the charges. Of course, there has to be a field which is taking these charges, and the velocity of charge is given by this. So from my definition of current density, it is current per unit area, right? So in this case, J is rho v times u. This is true in general. This is true in general for convective current, convection current, or conduction current. Of course, conduction current, you can specifically find out what is the charge density. For conduction current, you can say that, okay, let's say there are n electrons per unit volume with a charge E, then the force experienced is by the charge is negative minus E if E is the electric field, right? I say conductor is a where there are large number of free electrons. Say the n is the number density. Then the force experienced is this. I can use Newton's laws and say that the rate of change of momentum of the electrons is this force. And why would the momentum change? If I consider this as a solid, you have let's say an electric field. In the direction of the electric field, the free electrons would start moving, but they are able to move up to a certain distance, after which they start colliding with some other electrons. And so your momentum, there is a rate of change of momentum, there is a initial velocity and there is a final velocity. So if u is the drift velocity, which is the velocity with which the electrons are drifting in the conductor, and tau is the collision time, which means it is the time for which the electrons are able to move before they get collided or change their momentum changes. So in that case, the rate of change of momentum is simply mu by tau, change in velocity over time, is minus EE, in which case you have u as minus EE tau by m. So I could go back and write the general expression for just whether it's convection current or conduction current. We said J is rho v times u. So rho v times minus EE tau by m, and volume charge density we can write, if n is a number of electrons per unit volume, we already said minus E is the charge of the electron, then rho v is n times minus E times minus E tau by m. All these constants can be clubbed together, and that is what is written as sigma. So sigma is n E square over m. So this relation is J is sigma E, which is Ohm's law, by the way. There is Ohm's law written for electric field. This is true for conductors. Why? Because this is coming from this basic idea of collision and time of collision and applying Newton's law within the conductor. Whereas for convection current, I would just stick to this. I would just stick to this because it depends on the volume charge density in the ionosphere, velocity, depending on whether there is collision or not, you could either apply this, not apply. So that's about current. So current density is related directly to the electric field, applied electric field, proportional to the applied electric field, and that constant of proportionality is your conductivity. Okay, we will stop here. Just to summarize what we did today. The first thing we did was to review the idea of divergence, get to Gauss law in both the differential and integral form. I told you when should I use a differential form and when should I use the integral form. Then we went back and looked at it and said that it is not electric field because electric field is dependent on the material. So we should be writing this for a material independent quantity. So Gauss law gets written not just for, it's not for electric field, but it gets written for electric flux density, which is related to electric field as D is epsilon E. We wrote the Gauss law for the point form and the integral form. We defined electric potential, which is again a consequence of field, or rather to say that if I were to move a charge in the presence of field, I need to apply a potential. And that gets stored as the potential energy, just that, and we remembered the example of gravitational field and gravitational potential. Now if I do not have a potential applied, or I think about electric field applied to a region where there are large number of charges, what I can have is an electric current, and we discussed what could be convection current, what is conduction current. Displacement current is something which we did not discuss, we will do it in the next class. And we tried to see the importance of defining J as a vector, current density as a vector, and told you how to calculate current given J. Also told you in conductors we derive the Ohm's law. Now you can write this in terms of potential, that will give you the V is equal to IR form. Now in the next class we will talk about magnetic field, magnetic potential, and the next Maxwell's equations. We stop the class now. I am opening the session to questions. So if you have any questions, please hand raise or ask in the question window or chat window. If there are any questions, please hand raise or ask it. Write it down in the question window or chat window. ECABD, what's your question?
Morning, ma'am.
Ma'am, my question
morning.
is, what do you mean by convection current? Good morning, ma'am.
Yeah.
Ma'am, my question is, what do you mean by convection current?
Okay. So we define convection current different from conduction current based on where the current is flowing. Okay. If it is an ionosphere or there are free charges where there are free charges present and you are applying an electric field, you can't think about a conductivity for that, right? But you still have electric current flowing because if I apply a field, the positive and the negative charges would start following the direction of field. So in such situations, you define convection current, where the charges physically move from one end to the other. You are able to accelerate the charge. Whereas think about a situation like a solid in a conductor. There are free electrons which are moving around with a certain drift velocity, which contributes to conductivity of the material. In such cases, your current, which is, or the electrons which are responsible for the conduction of electric current from one end to the other, in such cases you call conduction. Is that clear?
Yes, ma'am.
Yeah. TCE.
Good morning, ma'am. Good morning, ma'am.
Good morning.
Good morning, ma'am. You have
Yeah,
told
please
that
ask
the
your question.
surface is perpendicular to the current charge density.
Hmm.
What will be the direction of current when the both are perpendicular to each other?
Both means the surface and the J.
Yes, ma'am. Surface is in the right direction, means if the current density is in the left direction, what will be happening to the current?
Oh, you mean 180 degree out of
180-degree phase shift, like that instance.
yeah. So question is, for the benefit of others, let me just repeat. Let's say I have a surface and the outward surface normal is ds. I have a current which is in this direction. This is what you're asking, right?
Yes, ma'am.
So in this case, I do have, when I calculate j dot ds, I will have j ds cos theta, and here theta is 180 degree, which means it will give me j ds answer with a negative direction. Negative indicating that the current flow is in the opposite direction to the surface normal.
Okay.
All right? Okay.
Thank you, ma'am.
So RVIT, please ask your question on the question tab. Okay, let me go to the question tab. Okay, one question from Government College of Engineering, Bargur is, in dielectric material there is no flow of charge. How is there possible of displacement current? So that is exactly where displacement current applies. In a convection current applies in a situation like plasma. Conduction current applies in a situation like a good conductor. But in dielectric material, the current flow happens through displacement current. As I promised, this will be discussed in the next class. PSG, what would be the typical value of drift velocity? Depends on the material again. The values are, few meters per second. MLVGC TEC, what are the limitations of Gauss law while applying any problem? Well, there are no limitations for Gauss law. The only thing that you want to take care is that the surface over which you are applying Gauss law is a symmetric surface about the charge. If you are able to find a symmetric surface, that would be the ideal case. Otherwise, you have to do it numerically. SGSIT, what are the limitations of Gauss law? If there are, give me an example. So the same question I can point out, tell you in the picture. Let's say I have a charge Q, a surface like this. I can use very nice symmetric surface because my charge distribution is symmetric. But let's say I have a charge distribution which is along this line. Let's say I have a charge distribution along this line. It's very hard to find a symmetric surface around this, which means I'll have to break it down into smaller problems. I'll take this, I'll take this, I'll take this, and I'll take this, and I have to do it independently, apply superposition, and then use Gauss. Right? So that would be the limitation. So in principle, it's not the limitation, it's how smartly you can solve the problem, understanding the Gauss law. RVIT, are you connected? No. PCE, did you have a question?
No questions, ma'am.
Okay.
Thank you.
Any other questions? All right, so I hope I have answered. This is a section or a topic which when you think about, you might still get more questions. Please email me if you have any further questions. See you next Tuesday.